You ask an AI model to add 36 and 59, and it tells you the answer is 95. Then you ask it how it arrived to that solution, and it explains that it carried the one just in the same way you learn it in school. But that's not what happened in reality. Inside the model, there was no carrying going on. Instead, two parallel strategies ran at once. One estimating the route answer and another calculating the final digit. So if the AI got the math right, but has no idea how it did it, the question is, what else is it doing that it cannot actually explain? That gap between what an AI model says and what it does is one of the most relevant problems in AI safety, in my opinion. I decided to make this video after reading the new research report from Anthropic that changes everything we thought we knew about how AI thinks. So in this video, we are gonna cover first the new techniques that researchers and engineers use to look inside a model's brain. Second, how Claude thinks in abstract concepts and plans ahead when writing. And third, why a model's step-by-step reasoning can be a complete fabrication. And fourth, and finally, the surprising counterintuitive reason why even the latest models still hallucinate. So let's dive in. So how do you build a microscope for an AI? The core problem is that looking at individual neurons doesn't tell you much. A single neuron might activate for basketball, round objects, and the color orange, for example, all at the same time. And this is called polysemanticity. And it makes the raw network activity impossible to interpret. It is like trying to understand a song by listening to the raw electrical signal going into the speakers. From that perspective, it's just noise, but what you actually want is the actual music. Anthropic's solution to explain this is to find that sheet music by decomposing neural activity into features. Features, in this case, are interpretable units corresponding to concepts, like the concept of something being small or the concept of person. To find a golden retriever feature, for instance, they show the model 100 pictures of them. The goal is to find the single knob inside the network that consistently activates for those images and nothing else. That knob is the feature. They study a simplified copy of Claude where raw neurons are swapped from these clean features, which still produces the exact same output. And this feature-based map lets them trace how concept connects, creating wiring diagrams for specific computations. But here is where this approach gets really powerful. Researchers can intervene during this process. They can reach into the model and manually suppress or inject a specific feature. Then watch how the output changes. For example, if you suppress the feature for rabbit and the model writes a different word, that is a strong causal evidence that the rabbit feature was doing exactly what you saw. And this ability to run controlled experiments is the key to truly understand its internal mechanics. And after many rounds playing this way, the researchers found that those mechanics get very, very strange. Let me explain. So, with this microscope in hand, you can test different hypotheses. For example, Claude speaks dozens of languages. Is there a separate French Claude and English Claude running internally? Well, the answer is no. When researchers prompted the model with the opposite of small, in both English and French, they watched what happened inside. The exact same core features were activated. Features for smallness and oppositeness lit up, regardless of the language used. These shared features then trigger a concept of largeness, which finally got translated into the specific language required for the output. This implies that Claude operates in an abstract conceptual space, where meaning exists before the language. This ability goes beyond simple concepts. It also extends to planning. Let's consider a couple of sentences that Claude wrote. He saw a car road and had to grab it. His own hunger was like a starving rabbit. To write that second line, the model has to make sense in context and rhythm with gravity. The researchers' initial hypothesis was that Claude writes word by word, and at the end of the line, it picks a word that rhymes. But that is not what they found. The microscope showed that Claude planned ahead before writing the second line at all. It had already identified rabbit as a candidate ending word. It picked the destination first, then wrote the line to get there. The intervention experiments confirmed this. When the researchers suppressed the internal rabbit features, the model rewrote the line to end with rabbit instead. They were able to prove that the model wasn't just generating text, it was making a plan. But what happens when this internal process doesn't match the story the model tells us? That's where things get much more concerning. So let's go back to our initial math problem. 36 plus 59. When you ask Claude to explain how it does it, Claude describes the standard Kerning algorithm we all learn in school. But when we look closely, we can see two computational paths running in parallel. One path estimated the raw magnitude, placing the answer between 88 and 97, but the other path focuses only on the last digit, computing that 6 plus 9 ends in a 5. And these two paths combine to produce the correct answer, 95. This is definitely not the same as the process that Claude described to us when we ask it. So why does it give the wrong explanation? Well, because Claude learned how to do math and how to explain math through completely separate processes. The explanations come from absorbing human written text where people describe the standard algorithm, but its actual computational strategies emerge on their own during the training. And this is a critical finding. It means that a model's self-report about its own reasoning can be inaccurate. Not because it is lying, but because it literally does not have access to its own algorithm. And when we ask a model to show its work, we might be generating a plausible reconstruction, not a faithful record. This harmless fabrication on a simple problem hides a much bigger issue on hard ones. Researchers found that when a model produces a chain of thought to solve a problem, that reasoning is not always genuine. On an easy problem, the microscope showed that the written out steps match the internal computations. But on a hard problem, something different happened. Claude produced a detailed chain of thought that claimed to work through the calculation step by step. The microscope revealed no evidence of any calculation happening internally at all. The model had generated an answer and then constructed a plausible looking justification after the fact. So in the end, this is not lying, because lying requires knowing the truth and contradicting it. This is producing statements without any concern from whether they are true or false. It is reverse engineering a justification for a predetermined result. Amazing, isn't it? So basically, LLMs are unreliable by design. So let's have a look at hallucinations then. The common view is that models can think up because they are completion machines. Anthropic's research turned this idea completely upside down. Inside Claude, refusing to answer is actually the default behavior. Researchers found a specific circuit that is always on there, causing the model to state it doesn't have enough information. So why does it ever answer then? Well, a separate mechanism is responsible. When the model recognizes a well-known entity in the prompt, say, for example, Michael Jordan, a known answer features activates, and this feature inhibits the default refusal circuit, allowing Claude to provide an answer. So hallucinations happen when this recognition system misfires. And if the model sees an unknown named person like, for example, Cesar Soto Valero, my name, the refusal circuit should win. But if the answer is vaguely familiar, the known entity feature can misfire, suppressing the refusal. Now, with the safety default disabled and no actual knowledge to draw on, Claude invents a plausible answer. So hallucination isn't the model being reckless. It is the recognition system overriding a safety default that was working correctly. And this tension between having to deal with internal systems explains certain jailbreaks. Researchers triggered Claude with an acrostic prompt, the following: babies outlive mustard block. Asked to spell out the first letter of each word, it started spelling B-O-M-B and been providing instructions before realizing it has been asked about bomb making. Safety features activate. The model recognizes it should refuse, but features that promote grammatical coherence exert a competing pressure. Once Claude has begun a sentence, these features push it to complete it. The safety features want to stop, but the grammar features want to finish. It is a battle. Grammar temporarily wins. Only when it reaches a natural sentence boundary can the model pivot to the refusal it was trying to give all along. In other words, the features that make Claude a very good writer becomes the vulnerability. So, what does all of this mean for us? Well, these findings paint a new picture on how an AI thinks. It is not a unified mind, but a collection of competing circuits for things like grammar, safety, and reasoning. What we see on the surface is just the negotiated outcome of these internal forces. Researchers are clear. These tools are new and only capture a fraction of the model's computation, but they represent a fundamental shift. So next time you ask an AI to show its work, treat the explanation with a healthy dose of skepticism. Ask yourself, is this a genuine trace of its internal process? Or is it a plausible story it is being constructed after it already knew the answer? Understanding that difference is the first step towards building AI we can actually trust. And if you want more deep dives into how AI works in reality, consider subscribing to the channel, because that way is how I know that this content is valuable to you. Thank you very much for watching and see you in the next one. Bye.